We will now examine major research efforts taking place over the last decade, both of which bear on our problem, in that if we can't predict earthquakes, at least not reliably, how can we continue our studies to try to do a better job so potentially maybe at some point in the future we have sufficient data to be able to predict earthquakes? Also, if we can't predict it, how can we at least give a warning? And so we will look at two major research efforts. One that's called the San Andreas Fault Observatory at Depth, with the acronym SAFOD. And we'll first do that using some excerpts from two videos. One video, the KQED Quest program, a program on earthquakes breaking new ground, as well as a video, San Andreas Fault Observatory at Depth, produced by the International Continental Drilling Program. I have merged these two together to try to give you the story on the nature of this particular research program to study the San Andreas Fault at Parkfield by drilling down into the earth and drilling the San Andreas Fault.
The North American and Pacific plates, which are constantly grinding past each other. The strain from the movement builds up along faults or cracks in the Earth's crust. When the strain becomes too great, the fault slips, releasing energy in the form of seismic waves, which produce the shaking we experience in an earthquake.
We have nucleation events, in other words, beginnings of earthquakes that happen all of the time. And we need to understand why one little beginning of an earthquake runs away to produce a big one. That's the big challenge that seismologists are facing.
So to answer this big question, scientists are thinking small earthquakes, that is, which originate miles below the Earth's surface.
Our challenges are a little bit like what it would be to do astronomy in a coal mine. First thing the astronomer might want to do is drill a hole to the surface and put a telescope up there, and that's essentially what we're doing at SAFOD. We're getting that first look inside the earthquake engine.
SAFOD, or the San Andreas Fault Observatory at Depth, is an experiment funded by the National Science Foundation,
hoping to answer fundamental questions about earthquakes and earthquake prediction.
We're here in Parkfield drilling a scientific borehole into the San Andreas Fault to directly make measurements of the physical and chemical processes associated with earthquakes actually at depth where they're happening.
We can learn a lot about earthquakes from the surface. We can understand how they propagate, how strong the shaking is, but we can't learn how they start. To understand the mechanics that begin earthquakes, we have to go where the earthquakes occur. And that's the goal of this experiment.
Unlike the parts of the San Andreas Fault that only rupture occasionally in large, destructive earthquakes, this stretch of the fault creeps along steadily and produces many small, harmless earthquakes. What is it about this part of the fault that lets earthquakes start so easily? Answering that question could be a major step toward knowing if earthquakes are predictable.
There are a great many theories that have been proposed by scientists about how earthquakes get started. Is there a fluid pressure change that gives the earthquake a push, pries the fault apart a little bit, and it takes off? Does the fault start to creep quietly a little bit before, get a head start before it takes off and produces an earthquake? To really test these kind of theories, you have to drill into the fault zone or be very close to it to actually measure, for example, fluid pressure changes that might occur right before the earthquake starts.
We're actually trying to drill into an active fault that regularly produces very small earthquakes, but nonetheless earthquakes that are big enough to teach us about how earthquakes work. And we're going to be making the measurements under the conditions under which those earthquakes occur. We're going to exhume the material, the two sides of the fault that produce that earthquake, and we are going to monitor that earthquake with instruments that are right up next to the fault, watching what happens as these earthquakes occur.
SAFOD is located in Parkfield, 95 miles south of Monterey. Since 1857, earthquakes have been recorded there with surprising regularity.
By having identified one of these areas where these small earthquakes recur very regularly on exactly the same part of the fault and produce exactly the same earthquake over and over again, it's almost like a natural earthquake machine. We will be able to watch the earthquake nucleation process many, many times in the future with different kinds of instruments, and eventually have a fairly complete understanding of what happens in a fault zone as an earthquake is about to happen.
To test their theories, the scientists are drilling down to more than 3 kilometers below the surface. The drill hole starts on the Pacific plate and crosses the fault at an angle to reach the North American plate. It penetrates the fault directly in the zone where the rocks break repeatedly in hundreds of small earthquakes every year. Having drilled into the fault, the scientists are, for the first time, bringing up rock samples from an active fault zone at the boundary between two tectonic plates.
For the first time, the SAFOD team has succeeded in extracting core samples from the San Andreas Fault. This sample was buried deep underground. Now it's being studied to learn how seismic activity helped shape its rocky DNA through millions of years of earthquakes, great and small.
By retrieving core from the San Andreas Fault, we now know what it looks like. What we found were thick zones of crushed up rock with a slippery mineral called serpentine, chunks of serpentine floating within this crushed up fault zone. Serpentine has long been suspected to be associated with how the San Andreas Fault moves in Central California. We see it exposed at the surface in the rocks that are adjacent to the fault, but now we know it's inside the fault and actually controlling how it works.
Detailed measurements of the San Andreas Fault will continue for many years.
We're going to deploy seismometers and other instruments, and for 20 years we'll be monitoring earthquakes at this site with instruments located right in the fault zone.
The SAFOD team drilled 2 miles below the Earth's surface to place seismometers directly inside the fault zone. These sensitive instruments measure seismic activity around the clock.
The earthquakes we're studying, these small earthquakes, bridge the gap between those laboratory and theoretical studies and the real Earth. We can actually determine how applicable those laboratory tests are, the theories based upon those tests, to real earthquakes that occur on the San Andreas Fault. And once we've confirmed those theories, we can then scale them up and apply them with confidence to even larger faults and the kinds of earthquakes that pose danger to the public.
But what the public really wants to know is if studying small earthquakes at their source reveals how to predict larger, more damaging ones.
Perhaps our monitoring instrumentation will detect changes within the fault zone that tells us that an earthquake is coming. That would be truly wonderful. And with these instruments, we'll be able to watch earthquakes begin over and over again, and perhaps we'll see signs that the earthquakes are coming. Perhaps we'll see that earthquakes are predictable. But even more basic than that, earthquake prediction is based on ideas about what happens inside a fault. And we have very little direct knowledge of what happens inside a fault. And that's why the question of whether or not earthquakes are predictable is so difficult to answer.
You'll learn more about in your reading assignments. There's a fact sheet that I would like you to read as one of your required reading assignments. And equally important will be a video about the cores themselves and the types of analyses that are carried out on those rock cores. So make sure you review the fact sheet. And even more importantly, watch the video on analyzing the cores, because that may well be a question on your upcoming unit exam.